Here's the really cool ring launcher. It's got a little on button here. I got an aluminum ring. Gonna put it right on this coil. Let's see what happens. Ooh, shot right up. Check how high this thing's gonna go. Welcome to Magnetic Induction Part 2. The aluminum ring, it's not magnetic. This is a magnet, nothing's sticking. So we have the aluminum ring sitting on top of the coil. Let's see what happens when we close the switch. As this is the positive side of the battery, the wire looks like it's going behind the cylinder, comes around this side, so the current is going to flow around like this. And using the right-hand rule, I put my thumb in the positive direction. My fingers will curl down through the coil. That's going to make this end of the coil a south pole. Now, it's not the fact that that's a south pole that's going to cause something. It's the fact that there was a change in the pole. Before this switch was closed, there was no pole at all. Closing the switch gave us a south pole where there was none before. So that's like having a south pole getting stronger. That would be the same thing as if you could imagine taking a magnet with a south pole and bringing it towards the aluminum ring. That means the current is going to have to produce a south pole on this side of the ring to oppose the approaching south pole from the coil. And those two repelling will cause the aluminum ring to go upwards. All right, let's try it again. Uh-oh, it didn't work. It's not going. How come? Because this ring has a split in it and the current can't pass through. So if you can't get the current to flow, you're not going to get the opposing pole. Ah, my motorcycle gang rings. So which one do you think is going to go higher? First, we'll use the big boy. Ooh, went right off the screen. Now we'll try the skinny guy. Oh, didn't go as high. Now you might have thought, well, hey, this is definitely lighter. It should go up higher. But keep in mind that this one here has a lot more places for the current to flow. So we're going to get way more current. And that overcame the fact that it's heavier. Yeah, this one I got at the Sturgis rally. It's made out of copper. Boy, let me tell you, is it heavy. But it's the same size as the aluminum one. It doesn't go up as high as the big aluminum one. Well, it's going to have the same conductivity just about. It's a good conductor, but it weighs way more. So you get the same amount of current with way more weight, not going up as high. Now, I know what you're thinking. What can we do to make this go up even higher? How about we improve the conductivity of the magnetic field lines with a shaft of soft iron? We're going to put that right down here. Now we're going to put this on top. Let's see what happens. Oh my gosh, it hit the ceiling. Okay, here it is, ready to go. Watch the ceiling. Oh man, like a bullet. That tells us that the strength of a magnetic field can depend on the material that the magnetic field flows through. Soft iron, real good conductor for magnetic fields. Okay, so what am I talking about? I got a paper clip here, and I've got a nice strong magnet, and as I bring it near, it doesn't do anything to the paper clip. Okay, I've got the magnet up here. It's certainly not going to attract the paper clip at that distance. And I've got the soft iron, and I'm going to put that on it. It doesn't do a thing to it. This is not a magnet. But if I put it on top of it like this, the magnet goes on top of the shaft of soft iron, and now I bring it near. Oh, look at that, magic. It picked it up. Now when I take the magnet off, hey, the magnetic field lines were conducted along the length of the iron. All right, now check this out. I've got a light bulb. The light bulb is connected to a coil of wire. Coil of wire has got a nice hole in here. We're going to put it on top, and we'll see if we can detect any changing magnetic fields. Ready? I'm going to turn it on. Nothing. Hey, maybe we need to increase the strength of the magnetic field by putting the shaft in here. Oh, hey, how about that? It really worked nicely. Notice how the light bulb stays on while after I keep the switch depressed. Hey, that means this thing's got to be running on AC. Because if it wasn't AC, that light bulb would have gone on for a brief moment and then gone out because there'd be no more changing magnetic field. The changing magnetic field induced a current in the coil, causing the light bulb to light up. Now, this is the basis for a wireless charger. The current of the coil is not connected to this current. There's no physical connection here. So we have induction causing this to happen. And that could have been a battery, and we could have been charging it up. Of course, we would need a rectifier to straighten out the AC current. Okay, let's take a look at a similar situation. We have here the conducting rails, a battery, a resistor. We have a wire that can easily move back and forth on these frictionless rails. Let's say the magnetic field going into the board is 3 Tesla. Battery is 5 volts, 4 ohm resistor, and this length from rail to rail is 15 centimeters. Let's find out what the initial current will be in this circuit. Using Ohm's law, we have the full 5 volts going across that resistor, and we calculate 1.25 amps. Now let's find the magnetic force acting on the wire due to this initial current. Previously, we've derived this formula, ILB, for the force acting on a wire carrying current through a magnetic field. Plugging in 1.25 amps times 0.15 meters for the length and 3 Tesla, we get 0.563 newtons. We can see which way this is going to go when you put your thumb in the direction of the positive current, your fingers into the board, and the magnetic force comes out to the right. But watch what happens next. As the current is flowing this way, that magnetic force is going to move the wire this way. That means these positive charges now have a secondary velocity compared to primary velocity that we just talked about. We can apply the right-hand rule once again. We put our thumb in the direction of positive motion, fingers in the direction of the B field, and now there's going to be another magnetic force, which I'll think of as the secondary magnetic force. So how could we calculate this secondary magnetic force? We can say Q, V, B. And the V and the B are still perpendicular to each other. If I divide both sides by Q, we can see then that we've just determined the electric field induced by the velocity of the wire through the magnetic field. This electric field is in this direction. It's in the direction of the force. What do I get when I take the electric field and I multiply by that length? That's a voltage. And again, that's what we've called the EMF, the electromotive force. Remember, it's not a force, it's a voltage. And what is the direction of that voltage? The battery is trying to make the current go clockwise, but this voltage would be the other way. It would oppose that voltage. That's going to reduce the amount of current flowing in the wire. So we're going to calculate the EMF that's going backwards, which is what we call the back EMF. I'm just going to make up a number, 4 meters per second. So let's say the wire is speeding up and it reaches 4 meters per second, 3 Tesla, 0.15 meters length. What would be the EMF back? All right, we get 1.8 volts. Now that's an induced voltage. Well, let's see what that does to our current. We'll use Ohm's law again for this resistor. But now what will be the voltage across that resistor? We're gaining 5 volts. And then we have to go across the back EMF, which is 1.8 volts. 3.2 volts, I, 4 ohm. We now have 0.8 amps flowing through this circuit. Well, I now have a new current. Why don't we figure out what the magnetic force is acting on the wire now? Hey, I only have 0.36 newtons acting on this wire, whereas I had originally 0.568 newtons. So what this tells me is the wire is still going to speed up. It just won't speed up as quickly. So let's say the wire continues to speed up. Watch what happens when it reaches 11.1 meters per second. Boy, that's almost 5 volts. Well, if we gain 5 volts from the battery and we have to go across 5 volts the wrong way, we're not going to have any voltage across that resistor. This is going to cause the current to approach 0. When the current approaches 0, ILB, you're not going to get a force. The thing can't speed up anymore. It's just going to keep on moving at a constant velocity. And we say we've reached terminal velocity. So when the back EMF equals the voltage of the battery, you have zero current and you can't go any faster. That's how you calculate the terminal velocity. And this, of course, is a motor. It's going to convert electrical energy into kinetic energy. It's the exact opposite of a generator. Now, what do you think is going to happen if this wire was moving along and I reached out and grabbed it and wouldn't let it go anywhere? That velocity is going to be zero, which means there won't be any force holding the charges back. That means there won't be any back EMF. If there's no back EMF, you're going to get a surge of current through here. And if you hold that there long enough, this thing's going to overheat. The wires can actually melt. The battery will go dead. Let's apply this to your vacuum cleaner. You plug it into your living room, you turn it on, and the lights dim. What's going on? Well, the motor hasn't gotten up to speed yet. It's not moving at all. So there's no back EMF and there's a big surge of current. Well, that takes the current away from the lights and the lights dim. But that's only momentarily, because once this thing starts to move, it'll generate the back EMF and you'll use less current. All right, you're vacuuming along and you pick up a sock. Hey, it gets stuck. The lights dim. Hey, they're going to stay dim unless you turn that vacuum off, because it's like me holding this wire and then it's going to be a surge of current going through there. So this is basically how your motor works in a very simple way that you have to make at home. Now, just a warning, some people think that because this wire starts to move, that force is going to be big enough to make the current actually go the wrong way. No, it won't. That voltage is making the current go this way, but the back EMF will just oppose that so that you get less current. It won't go the other way. If you think about it, it's a lot like air resistance. We release the object, it starts to fall. We pick up some velocity, and we get some air resistance. That air resistance isn't going to make this ball start going up. It just makes it accelerate slower. As the velocity increases, the friction increases until it reaches the weight of the object, and then we don't go faster at all because the net force is zero.